Okay, last page of chapter 10 notes, and really just one more issue we want to describe a little bit. And this I mentioned a little bit in the last video when we were talking about the liquid to gas transition, that if this is happening at a specific temperature, it's called the boiling point, but at lower temperatures, it might be called evaporation. And evaporation really is a consequence of this property of liquids called vapor pressure. So a lot of liquids, there's a pressure they produce where the liquid is converting into the gas phase. So as a result, you can counteract that pressure to maybe stop the liquid from evaporating. So I have the definition of that here. Well, it's not really a definition, but a description. The liquid to vapor transition can occur even below the boiling point of a liquid. So you may be familiar with materials like paint thinners or paint strippers or even something like nail polish remover. If you spill it, it evaporates really quickly, right? Sometimes before you can even get the rag to kind of wipe it up, it's already evaporated. So any liquid that has a really strong smell is probably evaporating really quickly. So the molecules are making it inside your nostrils where your scent can detect them. And if a liquid is really quickly converting from liquid to gas phase, there's a couple terms here that we would use to describe it. So volatile or volatility. So volatile would be the adjective form. We would say it's a volatile liquid if it evaporates really quickly. We would describe that in noun form as the volatility of the material. So things like gasoline is a pretty volatile material. It will evaporate fairly quickly if you just leave it out at room temperature under its own devices. Now, there is a kind of subset of vapor pressure called equilibrium vapor pressure. This is what I was referring to before. There's a pressure exerted by the vapor in equilibrium with the liquid phase. So what would happen here is, say on a humid day, there's a lot of water in the air, but then a sample of liquid water also has a vapor pressure. So if that sample of liquid water's vapor pressure is the same as the pressure that would be exerted by the gas phase water, then there's no net movement of the water from the liquid phase into the gas phase. Molecules might still transfer back and forth, but the amount of liquid water would stay the same. And I think we've probably, most of us living here in North Carolina have probably all experienced this. You go outside on a really humid day, you start to sweat, but that sweat doesn't evaporate. So when it's really humid outside, the sweat can't evaporate, which is what cools you off, is the energy change from that liquid going into the gas phase. You go outside on a dry day, if you've ever been out west, say Utah or somewhere like that, where you're at a high elevation and it's very dry, you don't even realize that you're sweating because your sweat evaporates so quickly. It might be 100 degrees, it doesn't feel bad because your body is cooling itself. You just get dehydrated really, really quickly. Okay, now we want to do some calculations on this equilibrium vapor pressure idea. All right, so I have one example calculation here. So then let's look at it. We have a half a gram of pure water. It's sealed in an evacuated 5-liter flask. So evacuated means we've used a pump to remove any other vapor out of there. So it would just be the water and whatever gas is formed as the water evaporates. We heat this up to 60 degrees. We want to answer the question as to whether or not the water evaporates. Okay, so let's draw some pictures here and think about what's happening in this situation. So here's a round bottom flask. And we've evacuated, so sealed at the top. We've evacuated all of the gas, and there's just this little sample of water at the bottom. So what's going to happen here is vapor pressure. This liquid, some of those molecules of water are going to transition into the gas phase. They're going to kind of push up from the liquid phase into the gas phase. So what's going to happen is some of that liquid is going to transition and be a gas. So there's the flask. Maybe this gets a little smaller. That would probably be hard to tell from my drawing. But there's some gas phase molecules of water here. And I made them like little birds because we know water is bent. So now there's some water in the gas phase. Well, now there's two pressures. There's the vapor pressure of the water pushing to evaporate. But there's another pressure now from the gas phase. So H2O in the gas phase also generates a pressure. Now, if these pressures are the same, evaporation is going to stop. But if the vapor pressure is larger than the evaporation pressure, then more water is going to evaporate. So this leads us to two different possibilities. Right? One possibility is that we reach that equilibrium. So that might look like this. A little more water evaporates than in the first one. Right? So there's a few more water molecules there in the gas phase. And now this pressure from the gas phase water is equal to this pressure, the vapor pressure from the liquid water. That would be equilibrium. Right? So if we have enough water, we'll reach that stage in our kind of sealed off flask. Now the other possibility would be that all the water evaporates. So no more liquid water, all the water evaporates, right? And all of the water would be gas. And this would be if we don't have enough water, not enough water to match the vapor pressure. So if all the water evaporates, but we still haven't generated enough pressure from the gas phase water to match the vapor pressure of the liquid phase water, the water will continue to evaporate. Now, with the information we have, we need to figure out which one of these is happening here. Now, if I look at the problem, I would start with the amount of water. We know there's a half a gram of water. Let's take that half gram of water and figure out how many moles of water that would be, because we're headed to a gas law calculation, and gas laws, we need moles of our sample, not mass. So we saw in one of the previous videos, in fact I think it was the last one, the molar mass of water, so let's not go through all the details of calculating that again. 18.02, that will tell us how many moles of water are in this sample. So 0.5 divided by 18.02. So 0.02775 moles of water. Now, we're limited here to 2 sig figs, but I'm going to keep a little extra information to kind of carry through the problem. Although, if you got your fancy calculator, you can keep that whole number through the next steps of the calculation as well. All right, now if we know how many moles of water there are, think back to the problem. We've got the temperature and we have the volume. So we would have N, T, and V, and that's enough information to solve for the pressure. So we know, hopefully, from last semester, PV equals nRT. If I rearrange that equation by dividing both sides by V, I can solve for the pressure. So pressure would be nRT over V. Now we just need to plug those in, and of course they have to be in the right set of units as well. We have our quantity of moles there before, so one of the assumptions I'm making here is I'm just pretending all the water evaporates. That'll give me some information in which to go on. Here, multiply by the gas constant, 0.0821 liter atmospheres per K mole, and times the temperature. Now temperature's got to be Kelvin. We were given the temperature as 60 degrees, right? The lazy writer of the worksheet left you with only one significant figure there as well. Let's pretend it's 3, just so we don't have to round to one significant figure at the end. To convert from Celsius to Kelvin, we want to add 273. So 60 plus 273 would be 333 Kelvin. And we've got to divide all that by the volume. The volume of our flask was 5.0 liters. Okay? Everything is going to cancel out there except atmospheres, which is our pressure unit. So let's plug that in. Now I'm going to retrieve the answer from the previous problem. Again, just so I don't introduce any rounding errors. And that gives me 0.1517 atmospheres of pressure. So if all of that water evaporated, it would make a pressure from the gas phase of 0.1571 atmospheres. 1517 atmospheres. Now, if that's, right, back up here, we want to see, is that lower than the vapor pressure or higher than the vapor pressure? Because that will be what determines whether we hit equilibrium or not. Now, the vapor pressure given in the problem was in millimeters of mercury. So we need to convert to one of these into the other unit so that it's easier to compare. So let's just take that answer, atmospheres, convert that to millimeters of mercury. So there are 760 millimeters of mercury in 1 atmosphere. Now, depending on the textbook you used for your Gen Chem 1 class, torr, millimeters of mercury are the same thing. So some textbooks tend to use 760 torr in an atmosphere, but they're completely interchangeable. So if you're used to that one, it shouldn't really change your convert calculations much. Times 760, that would be 115 millimeters of mercury. Right, so the pressure that could be produced if all the water evaporates is lower than the vapor pressure of liquid water would be at this temperature. That puts us in this situation. All the gas evaporates before the pressure is high enough to the point where we would cause this equilibrium vapor pressure situation to occur. So that tells us all water evaporates. Right? And that's the answer to our question. Now, this could be a more complicated question, right? More complicated, more fun, are synonymous. I think we can all agree on that. This would be a little more complicated if it was higher, right? So if we went through this calculation, we found that this was a higher value than 149.4. Now we know that not all the water evaporates, right? So now we might need to go through and figure out, once all the water evaporated to make that pressure, how much water was left over. Essentially, a similar calculation, we could take that pressure, plug that into our ideal gas law to calculate N, which would be how many moles of water it would take to get to the equilibrium situation. Subtract that from the number of moles of water we started with, and that would give us information about how much water was left over. Okay, that's the end of chapter 10. So next video, we'll start into chapter 11.